a piecewise function is a function that is made up of multiple pieces. So it's actually multiple functions all within the same function. So this function is called f, and it contains, this little bracket means that it contains everything inside that bracket. So there's two functions here, and I'm going to highlight the top one with green and the bottom one with blue. All right. Now there are conditions to these two functions. Right over here, these are the conditions. So when we're using x values that are less than or equal to 4, we use that top function, 2x plus 3. When we are using x values that are larger than 4, we use the bottom blue function, x squared minus x plus 5. And if you looked at this on a graph, it would actually be two different graphs on the same graph with a dividing line where it switched from one function to the other function. So let's say if I asked you to evaluate this function when x equals -2, which function would you choose when x equals -2? The top one. Why the top one? Because -2 is less than 4. What if x equaled 5? The bottom one. Use x squared minus x plus 5. Because 5 is larger than 4. Okay. What if x equaled exactly 4? Which one would you use? The top one. Because this symbol, less than or equal to, indicates that that function is used when x is smaller than 4 or when x is equal to 4. So, numbers 1, 2, 3, and 4, we have two little puzzle pieces to deal with. First of all, we have an f of x function. We also have an h of x function. So there's the f piecewise function and the h piecewise function. Each piecewise function has two subfunctions. So when we look at number 1, we need to first think about, it says f of -3. So we need to use the f function when x equals -3. So look at our f function, which has 5x minus 1 and x minus 9. If x is exactly -3, should we use the top or the bottom function? The bottom function. -3 is equal to -3, so we need to use, according to this condition right here, we need to use this bottom function, x minus 9. So f of -3, we would plug -3 in. -3 minus 9 is -12. Number 2. They're asking us to do h of 5. That means we're going to use the h function when x equals 5. So go to this big h function. If x is 5, should we use the top subfunction or the bottom subfunction? Top. So f of 5, oops, not f of, almost made a mistake there. H of 5 would be 1/2 times 5 minus 10. Just making all kinds of mistakes over here. Half of 5 is 2.5, and 2.5 minus 10 is -7.5. Okay, I want you to try 3 and 4 on your own. And if you feel unsure, dive in and try it. It's okay if you make mistakes. So for number 3, we're looking at the h function when x is -4. -4 is less than 6. So once again, we are going to use that top function. For number 4, f of 3, +3 is larger than -3. So we would again use that bottom function, x minus 9. When you go to graph piecewise functions, it's really helpful to use pencils so that you can erase the portions of the graph that you don't want. Now let's look at this graph for a minute. This first equation, 2/3 x plus 2, uses the x values larger than 2. The other one, -x plus 1, uses the x values less than or equal to 2. What I notice in both of these conditions is 2 is like the changing point between those two functions. So at 2, I am going to draw a vertical dashed line. You do not have to have this line, but it's a nice visual cue so you can think about the two sides of your graph and the two conditions of this piecewise function. The other thing I'm going to do is think about where on the graph are each of these functions going to exist. When x is bigger than 2, where on the x-axis is x bigger than 2? At 3, 4, 5, over here on the right. So this green function is going to be the function on the right side of this dashed line. The purple function uses the x values less than or equal to 2. So 1, 0, -1, and so on over here on the left side of that line. So that's going to be our function on the left. Once I've thought about that, I'm basically going to just graph both of these and then we'll erase what we don't want. So green function. It says our y-intercept is 2. So I would put my y-intercept at 2. Preferably in pencil, as we are likely going to have to erase some stuff. A slope of 2/3 means up 2, right 3, up 2, right 3, up 2, right 3. Once I kind of call this like the skeleton of the graph. We haven't drawn the line in yet, but we have the points. We could easily draw this line in all the way across our graph. But let's think about this green graph needs to be on the right side of that dashed line. So I know that I am going to keep this portion of that line. Now look at this point on the y-axis. Can that green function exist on the left side of that boundary line? So I'm going to erase that point. Okay, now we do want our line to go all the way to the boundary line. So here's what I'm going to do. Extend this line, and then I'm going to put an open circle here. That might be kind of hard to see, so I will try to make it easy to see. Now look back at the conditions for this problem. Can anyone explain to me why I used an open circle on that boundary line? So if you look back at this condition, right here, x does not include 2 on that function. So that x value of 2, the green line cannot have a point at 2. Now 2.00001, the green line can exist. But at exactly 2, the green line can't exist, so we use an open circle. Okay, now the purple one. -x plus 1. Let's graph this like normal. So if you weren't doing piecewise functions, we would put a y-intercept at +1. Our slope is -1. Do you know how to reverse your slope and go in the other direction as well? So you can extend your line up this way. And if you're looking at this and thinking, Mrs. Gilmore, why did you draw that on the right of that line? I know. I know, just chill. Once we have the skeleton of this line, now we need to think about where on the graph can this particular line exist. It is supposed to exist on the left side of our boundary line. So on the left side of this line, I connect my points and extend my line. On the right side, I erase those extra points. Now, I have a closed circle at that boundary line. Look back at the conditions. Why do I have a closed circle at that boundary line? It includes 2. So the purple line needs to include an x value of 2. The green line should not include an x value of 2. So now if you look at this graph, if you picked out an x value of -5, you'd look at that graph and you'd be able to find what that value is supposed to be. If you picked an x value of 6, you could find out what that y value is supposed to be. So this visually shows you what y equals for each x value in there. The changing x value, where it changes from one function to the other function, is at 4. So get that vertical boundary line drawn in at 4. That visually will help you separate your graph into the right side and the left side. X is less than or equal to 4. That's going to be left of that boundary line. So our green function is going to be on the left and our purple function is going to be on the right. So let's graph that first function. We start at -2 and use a slope of 3. And then think about that is supposed to be on the left side, is what we agreed, and it's less than or equal to, so that will be a closed circle on that boundary line. So that one's actually pretty easy because it takes you right up to the line. Graph your second function. Start at 6. And then think about which side of the boundary line is this one supposed to be on. It's supposed to be on the right side. So any of these points from graphing that were on the left side, oops, I think I erased more than I needed to. Oops, I erased my green line. It's easier when you have pencil and not an electronic thing. And then think about, should this dot on the boundary line be an open circle or a closed circle? Because it's plane greater than, that one needs to be the open circle. Notice one of your graphs will have a closed circle, the other one will have an open circle.